Problem 13. Problem 13 says a light beam of wavelength 510 nanometers shines on a particle of mass 7.8 times 10 to the minus 34 kilogram. According to Compton's scattering experiment, what will be the wavelength of the scattered light at an angle of 120 degrees? Okay, this concerns the very famous experiment by Compton. Compton's experiment was one of the cornerstones of quantum mechanics, and it showed that a light beam has particle properties such as momentum and kinetic energy. So basically the experiment consisted of shining a beam of light of a certain wavelength and also therefore a certain frequency, and then that was shown on a particle of mass m, and basically the mass m went off in a certain direction with a certain velocity and an angle theta, and then the wavelength of light was scattered at a different angle, okay, and this angle is theta. Let's actually call this phi. This is the angle we can call phi, and then this is theta, and then the frequency and wavelength of the light beam changed, okay. So one of the predictions from classical mechanics was that at a particular scattering angle, the frequency should have been a range of values. But one of the things this experiment showed is that at a particular angle theta, there was only one frequency corresponding to one wavelength. Okay, so that clearly showed that the beam of light carries a certain momentum. When it hits another particle, the particle goes off in a certain direction. The wavelength of the light changes by a certain factor because its momentum changes, right? So if we the conditions of momentum conservation and kinetic energy conservation, we have to use the relativistic momentum and relativistic kinetic energy conservation. The equations become what? The momentum initial equals momentum final. Momentum initial h over lambda, right? Remember, the momentum of a light beam is the Planck's constant divided by its wavelength, and then which is equal to, now in the x direction, we have to divide this up into x, right? In the x direction, the momentum is h over lambda. The x component of the momentum here is equal to h over lambda prime cosine of theta plus the momentum of the particle mass m, mv cosine phi, but we have to use gamma mv, right? Gamma being the relativistic factor for the particle, right? How about in the y direction? Well, in the y direction, momentum initial y equals momentum final y. The initial y momentum is 0. The momentum of this one is going to be gamma mv sine of phi. That's in the vertical direction, this momentum. And then the momentum vertical of this, that's negative h over lambda prime sine of theta. Okay, so we can actually equate them. Since they're equal to 0, I can say gamma mv sine of phi is equal to h over lambda prime sine theta. And then the kinetic energy conservation comes out to be equal to kinetic energy initial equals kinetic energy final. The kinetic energy of a beam of light is the same as its total energy, right? Because it doesn't really have rest energy. So the kinetic energy is just equal to E initial. And then the final kinetic energy is the final energy of the beam of light plus the kinetic energy of the particle of mass m. So the energy of a beam of light is equal to h times the frequency, the final beam of light, frequency f prime, and then the kinetic energy of the mass, gamma minus 1 mc squared. To be more specific, we could put here m0, we can add here m0, and we can add here m0, right? Now, let's relate this to the wavelength. The energy is hc over lambda. And this is equal to hc over lambda prime, gamma minus 1 m0 c squared. So here are my equations. Kinetic energy conservation. This is momentum conservation in the y direction. This is momentum conservation in the x direction. So if you think about it, this is sort of a continuation of the previous problems. Problem 12, problem 11, problem 10, momentum conservation, kinetic energy conservation in relativistic dynamics. And the Compton experiment is an outflow of that, right? If you put together all these three equations, you can derive the Compton equation, and the Compton equation is this. Over MEC, 1 minus cosine theta. So basically, I've eliminated the angle phi, and I've eliminated gamma. You eliminate phi, eliminate gamma, put all these three equations together, you can derive this. This is the mass of the particle, m0. Now, in Compton's original experiment, he used X-rays, because since X-rays have a shorter wavelength, the percentage shift of their wavelength from this scattered angle is more noticeable. Roughly speaking, the wavelengths that he used, lambda was about 0.071 nanometer. Okay, that's the wavelength of an X-ray. And then he used electrons, so the X-rays were shot towards electrons, so ME was the mass of an electron. This factor comes out to be equal to 0.00243 nanometers. Okay? But you don't necessarily have to do the Compton effect with that mass and with that wavelength. We can do some general wavelength like this. But in his case, angle, right? And then the wavelength of light would have bounced back at 120. It would have gone something like this, right? So this would be 120. And then we could solve for this angle phi if we want to. What would this have been? Lambda prime, if we use the data from Compton's experiment. Well, what we would have done is we would say lambda prime minus 0.071 nanometer is equal to, and then this one is given in terms of a nanometer, 0.00243, 0.00243, 1 minus cosine of 120. Okay? Notice what happens. Since cosine of an obtuse angle, 120, that's negative. So it has the effect of being added to 1. So the shift is greater for wavelengths that scatter backwards. And that makes sense, because that means the beam of light imparts more of its momentum to the electron, right? So this becomes a factor greater than 1. Okay, so let's try this one out. 1 minus cosine of 120, that comes out to be 1.5. 1.5. Because cosine of 20 is negative 0.5. So then you multiply that by 0.00243, and then you add 0.071 to it. Lambda prime is equal to 0.074645. And you could notice the shift is quite noticeable, from 71 to 74. So that's roughly about a 3 or in 7, 4 in 7, that came out to be about a 7% shift. So that's quite noticeable. Now, what would it be if we use our numbers? We're shining a beam of light 510 nanometers, so it's not an X-ray. It is actually a visible light, right, towards the blue range for 510 nanometers. So let's try that here. So it will be lambda prime minus 510 nanometer. Now, since we're not using the mass of the electron, we're using some other mass. This actually happens to be something even lighter than the electron. The mass of the electron, 9.11 times 10 minus 31. So you put the mass that you have, Planck's constant, 6.626 times 10 to the minus 34. The mass that we are using, which is going to be 7.8 times 10 to the minus 34. And the speed of light, this one, 3 times 10 to the 8. 1 minus cosine of 120. Well, we already know this is going to be 1.5. Right? So we're going to have 7 times 10 to the minus 9. Right? And that will be in units of meters. Well, what we could do, since this is a nanometer, I can say 1 meter is 10 to the 9th nanometer. Right? A nanometer is 10 to the minus 9 meter, right? So what ends up happening, this cancels this, meter cancels meter, and then it ends up just being 4.247. So what's the wavelength of the reflected light? 514.247. Okay? So that is still a little bit noticeable, because from 510 to 514, it'll be a little bit different shade of a color. What's the percent shift over there? If we wanted to calculate percent shift, then it'll just be a shift of what? Well, that's a shift of about 4 over 500. Make it into a percentage, what do? We multiply it by 100, and the 2 zeros cancel, and you have 4/5, right? 4/5 is 0.8%. So in the case of the X-ray scattering, the shift was about 7%. Here you are talking about a 0.8% shift. So not as noticeable, but it's still present, okay? So now you can see the Compton effect, how important it was in history. And from the Compton effect, we have the firm confirmation that any beam of electromagnetic radiation carries both momentum and kinetic energy, and it imparts that to a particle when it collides with it, okay? So thank you very much.